Somewhere in the vast darkness of space, there are places where the laws of physics as we know them seem to break down. We call them black holes, regions where gravity is so overwhelming that nothing, not even light, can escape. For decades, they existed only as a strange prediction buried in Einstein's equations. Today, we know they are real, scattered across the universe by the millions, silently shaping galaxies, warping time, and hiding secrets we are only beginning to understand. A black hole's story usually begins with the death of a massive star, one many times heavier than our Sun. For millions of years, that star holds itself up by fusing hydrogen into helium, radiating outward pressure that fights against its own gravity. But once the fuel runs out, that balance collapses. The star's core caves in on itself in a matter of seconds, triggering a supernova, one of the most violent explosions in the universe. What's left behind, if the core is massive enough, is a black hole. Surrounding every black hole is an invisible boundary called the event horizon. It isn't a physical surface, there's nothing to touch or see, but it marks the point of no return. Cross it, and the speed needed to escape exceeds the speed of light itself, which means escape becomes impossible. From the outside, we can never observe what happens beyond this boundary. The event horizon simply marks where our universe's rules of light and information quietly come to an end. At the very center of a black hole lies something even stranger, the singularity, a point where, according to Einstein's general relativity, matter is crushed into infinite density and zero volume. Most physicists suspect this infinity isn't the full picture. It's likely a sign that our current theories break down at such extreme scales, rather than a literal description of reality. A complete theory uniting gravity with quantum mechanics may be needed to truly explain what lies at a black hole's core, and scientists are still searching for it. Get close enough to a black hole, and space and time themselves begin to behave strangely. General relativity predicts that a massive object like this bends the very fabric of spacetime around it, and observations confirm it. Light bends as it passes nearby, an effect called gravitational lensing, which lets astronomers detect black holes indirectly by how they distort the light of stars and galaxies behind them. Time itself would also appear to slow down for anyone approaching the event horizon, at least as measured by a distant observer, a real, measurable consequence of gravity's grip on the universe. Not all black holes are created equal. While some form from dying stars, others, known as supermassive black holes, are millions or even billions of times heavier, and astronomers have found one lurking at the center of nearly every large galaxy, including our own Milky Way. How they grew so large remains one of astronomy's open questions. Some may have formed early in the universe's history and grown over billions of years by merging and feeding on surrounding gas and stars. Their gravity helped shape the structure of the galaxies that surround them. For most of history, black holes could only be inferred, never seen directly. That changed in 2019, when the Event Horizon Telescope, a global network of radio observatories working together, captured the first-ever image of a black hole's shadow, in the galaxy M87. 2 years later, the same team released an image of Sagittarius A*, the supermassive black hole at the heart of our own galaxy. These images don't show the black hole itself, but the glowing ring of hot gas swirling around its edge, visual proof of what physics had predicted for over a century. Black holes remind us how much of the universe still lies beyond our full understanding. They challenge our best theories, push the limits of what we can observe, and hint at physics we haven't discovered yet. Each new observation brings us a little closer to answering one of the biggest questions in science: what really happens when gravity wins completely? And in that mystery lies one of the reasons we keep looking up.